Our story begins 4.6 billion years ago in a corner of the Milky Way galaxy. A vast cloud of dust and gas, a nebula swirled under gravity. As it collapsed, it spun faster, like a figure skater pulling in their arms. The center grew denser and hotter, igniting into our young sun. Dust and gas orbited the newborn star, remnants from its formation. Over millions of years, particles collided and stuck together, growing larger. These clumps formed planetesimals, the building blocks of planets. In the swirling disk, planetesimals interacted, drawing together in a chaotic dance. Some were flung out while others collided, reshaping their destinies. In this chaos, Earth began to take shape. As Earth grew, its gravity attracted more material. This led to a young, molten Earth, bearing the scars of its birth. But the drama was far from over. A cataclysmic encounter awaited, altering our planet's fate and setting the stage for life. In the early solar system, chaos reigned. Planetary collisions were not uncommon, and Earth was on a collision course with a Mars-sized object we now call Theia. This catastrophic event, known as the Giant Impact Hypothesis, would shape our planet and its destiny in profound ways. Theia, hurtling through space, slammed into the young Earth with unimaginable force. The energy released in this collision was staggering, instantly melting the surface of our planet and vaporizing Theia into a cloud of superheated debris. This debris, a mixture of material from both Earth and Theia, was flung into orbit around our planet. Over time, this debris coalesced under its own gravity, eventually forming the celestial body we now know as the Moon. The impact had other profound consequences. It is believed that the collision tilted Earth's axis to its present 23.5 degrees, giving us our seasons. Perhaps even more significantly, the impact is thought to have dramatically sped up Earth's rotation. The length of a day on the early Earth, following Theia's impact, is estimated to have been a mere 5 or 6 hours. Imagine a world where the sun rose and set every few hours, where days and nights flashed by in a dizzying blur. This was the reality of early Earth, spinning rapidly in the aftermath of Theia's impact. The planet was a place of intense geological activity, its surface a molten sea punctuated by volcanic eruptions. The rapid rotation influenced everything from atmospheric circulation patterns to the distribution of heat across the planet. The oceans, still forming from condensing water vapor, were likely far more turbulent than those we know today, whipped into a frenzy by the planet's rapid spin. However, this breakneck pace of life wouldn't last. A combination of factors, most notably the gravitational influence of our newly formed moon, would gradually put the brakes on Earth's spin. Over billions of years, the length of a day on Earth would slowly stretch, eventually settling into the familiar 24-hour cycle we experience today. Section 4. The Moon's Influence, a gravitational dance through time. Since its formation, the Moon has been locked in a gravitational dance with Earth. This dance, while seemingly subtle, has had a profound impact on our planet's rotation. To understand this influence, we need to delve into the concept of tidal forces. The Moon's gravity pulls more strongly on the side of Earth facing it than on the opposite side. This difference in gravitational pull creates a bulge of water on both sides of Earth, forming the high tides we observe. As Earth rotates, these tidal bulges, dragged by the Moon's gravity, are slightly ahead of the direct Earth-Moon line. This misalignment creates a subtle tug, a gravitational brake that has been slowly but surely slowing down Earth's rotation over billions of years. Section 5. Tidal friction, the unseen force slowing Earth's spin. This gravitational braking effect is not a one-way street. As the Moon pulls on Earth's tidal bulges, it creates friction. This friction, known as tidal friction, dissipates energy primarily in the form of heat within Earth's interior and oceans. The energy dissipated by tidal friction comes at a cost: Earth's rotational energy. As this energy is slowly but steadily transferred to the moon, Earth's rotation slows and the length of a day increases. But the story doesn't end there. This transfer of energy also affects the moon's orbit. As Earth's rotation slows, the moon, in response, slowly spirals away from us at a rate of about 1.5 inches, or around 3.8 centimeters per year. This ongoing dance between Earth and the moon, a delicate balance of gravity and energy transfer, has been playing out for billions of years, and it will continue to shape the destinies of both celestial bodies far into the future. Section 6. A glimpse into the future when Earth's rotation winds down. Earth's rotation is slowing, a process that will continue for billions of years. The moon will drift further away, lengthening our days. Eventually, Earth and moon will reach synchronous rotation. 1 Earth day will equal 1 lunar month. The moon will appear fixed in the sky. Tides will cease, replaced by a permanent bulge of water. Days and nights will stretch, causing extreme temperature differences. Contemplating these changes highlights the dynamic nature of our universe.